So welcome everybody. Thanks for coming this morning. My plan this morning is to talk about kind of this interesting combination of machine learning, high performance computing, and humanities research. I think each of these three, are the domain of people with a great deal of expertise, and you could give a talk easily on any one of them for many hours alone. So to some extent, this talk might seem like a bit of a mishmash of different topics, but hopefully it gives you a sense of what the potential is for intersection between these three items. So I'm going to start out by giving a kind of a very broad strokes overview of machine learning. I'm not sure how many of you are already experienced with machine learning, but I'll kind of give this as a very broad overview. And I'll then talk about three topics that I've kind of cherry-picked from the literature within the past 2 years or so. So that this is pretty recent research showing research that incorporated elements from both domain expertise in some humanities field, along with machine learning, and then they did their computing on high-performance computing resources. So these three topics will be art attribution, listening to Danish radio, and looking at archaeological artifacts. When I've talked about this, then I'll kind of step back and give the broad strokes overview of high performance computing, just so that once we've seen these examples, we can think about how HPC might be useful in this particular context. And then I hope to leave enough time that I can open this up a little bit for discussion, because I would be very interested in hearing other studies that people are aware of or that you might be directly involved in, which involve the intersection of these three. I'll also give a little bit of a disclaimer. So I am very much more on the HPC and machine learning side than I am on the humanities side, but I do have a certain amount of exposure to literature that's been written in the humanities, but by no means am I a domain expert in the research that I'm going to be presenting. So if for those of you who are more familiar with these particular fields, I hope I don't make any goofs. So I'm going to start now just by giving a broad strokes overview of machine learning. Machine learning, broadly speaking, is a subset of artificial intelligence. Artificial intelligence, broadly speaking, is has the goal of trying to mimic the intelligence or behavioral pattern of humans or other living things. And machine learning is a subdomain within artificial intelligence. It focuses mainly on algorithms and statistical models, to perform tasks without explicit programming. Of course, there is programming involved in machine learning. But the programming that's used in machine learning is a little bit different than your conventional programming. Artificial intelligence can be approached in several different ways. One is, for example, if you just try and design an artificially intelligent robot, you could try and explicitly program it to behave a certain way, given the environment that it finds itself in. You could give it a set of rules as well as a set of logic to follow the rules that you've given it. So that's the domain of expert systems. That would be another way to encode artificial intelligence. Machine learning is very much on this third item that I mentioned, where you're trying to detect statistical patterns in some data set that you have in order to infer particular models that are appropriate to whatever data set it is that you've identified. So I said the programming with machine learning is a little bit different. Typically, say with scientific programming, say you're trying to simulate the evolution of a gas. You might take some set of input conditions, you write a computer program which will model the evolution of these molecules in the gas, and then you run your simulation and you get out your results, which is the motion of these molecules over time. The approach to machine learning is a little bit different in that you can start out, in a sense, with something here that I call results. You might start out with data. You already start out with results which have been associated with the given data that you're looking at. And the goal of the computation is to figure out which particular model or which form of the model that you've chosen is best suited to describe the relationship here between the data and the results. So if you think of this, say, just in the simple case of a regression problem, where you might look at a data set like this, and fit a polynomial curve to this. There's a dependent variable and an independent, and you might look at this data set, fit a functional form to this, and on the basis of the functional form that you've determined, you'll be able to take a new instance which has a new value for your independent variable, and be able to predict on the basis of the function that you fit what an appropriate value might be for the dependent variable for this new instance. These points here represent what I called the data and the results. So the data would be your set of features. The results would be the value that you're trying to predict. An example of how this might factor into everyday applications. So say you're trying to buy a new house on Zillow. Zillow will provide to you its Zestimate, which is its estimate for the price that a house might sell. And it bases this estimate on a variety of different conditions, such as the number of bedrooms, the number of bathrooms, square footage of the house, various things about the neighborhood. In this particular case, this is your dependent variable. Your independent variable or your features are all of these other things which feature into the price of the house when you're trying to sell it. So Zillow could do something like a regression analysis on the house sales, and it could try and offer then an estimate, its Zestimate of how what the expected sale price of the house would be on the basis of the features that it has. This would be a simple case for applying machine learning. Machine learning is, has been used in our everyday tasks for quite a while now, actually. Another case would be trying to classify your emails into spam. So there might be some large data set of emails, and there's some manual task beforehand where you identify which particular emails are spam and which are not spam. And then at some point on the basis of the data set that you've gathered, you have a data set here where you have your data, which are the emails, and the results, which are this binary class of being spam or not spam. And you can feed that into your machine learning algorithm. And it identifies, which classification model would be most appropriate to the particular emails that you've received and the classes you've assigned to them. So that if you get a new email coming into your inbox, now the model that's been trained on this particular data set could identify whether it should be put into your spam folder or just sent to your inbox. This was also useful for the post office, say when you're trying to classify handwritten digits that have been written on envelopes. Everybody tends to have their own unique handwriting style. So you get a very large array of possible styles for writing all of the different digits that you see on envelopes. But it would be very useful for the post office if they could simply, scan the envelope that they receive at the post office and have some automated way of trying to identify what the zip code is that's written on the envelope. So trying to do classification of images was very, of high importance to the post office in this particular case. It's also of relevance to financial institutions, say, if you're trying to encode the handwriting of dollar and cents numbers on checks in order to do automated processing of checks. Financial institutions are very interested in this, and they want it to be very accurate. They don't want you to be able to deposit or cash a check in an automated way, which isn't appropriate to whatever the representation is here for the particular handwriting. And this is being incorporated more and more into our everyday life. If you go to Netflix, it'll try and determine what, with what probability does it think you're going to give a high rating to certain products. And it does this, so that it can try and advertise particular shows for you to watch. And if it knows which ones you're more likely to watch, it's more likely to keep your business. It's more likely that you'll stay now attuned to Netflix rather than going over to Disney Plus or Hulu or some other service. Of course, Amazon has taken this even further. Amazon has its own streaming service, but Amazon has its entire suite of products now where it feels like you can buy everything on Amazon. So if now it can not only figure out which particular movies are you most likely to watch, but it can also figure out, that you have an animal, so it might try and sell you cat products. It'll might realize that you bought broccoli 2 weeks ago and that you're a consistent buyer of broccoli, so it tries to advertise broccoli deals to you. Amazon kind of brings this machine learning to you so it can advertise lots of different products to you and get you now to only come to Amazon for its particular services across a whole wide range of products. So machine learning is of high importance to businesses in terms of keeping track of their customers, trying to sell things to their customers, trying to figure out how they can price things appropriately to their customers so that they get the most profit but are also able to retain the customers. So there's any number of machine learning, or any number of reasons that machine learning can be used in business. Of course, it's also being used increasingly in many fields across UCLA and across across other academic institutions. In medicine, it can be used quite a lot. These are showing 4 different ways to apply machine learning algorithms to medicine. In some senses, it's just an abstract representation, but you could do something where you identify features. You might have patients and you do binary classification, to say whether they're at high risk for something. You might be able to ask them a set of questions on a survey, which are appropriate to what your machine learning algorithm has identified as a good decision tree in order to identify the risk. I'll talk about this particular picture shortly. This one is, you can also apply clustering algorithms. And any other number of models can be applied to medicine too. So image processing is a very interesting topic for machine learning. Neural networks, and in particular convolutional neural nets, are very good for trying to do pattern detection and, say, object recognition inside of these 2-dimensional or higher dimensional images. This also comes into play in any place where you're trying to do a recognition of patterns within images. So like if you have a photograph and you're trying to do facial recognition, this is an abstract representation of a convolutional neural net, which is a machine learning algorithm to try and identify faces. So I'm going to pause just a little bit because this is going to come up in the examples that I'm going to talk about, looking at neural networks and in particular convolutional neural nets. So that abstract representation is represented here. Very generally speaking, the object of the neural network is to take your image and apply a very high dimensional data transformation so that you can transform it into something which, say, is just a set of particular numbers. Here a much lower, much smaller in size and lower dimensional array at the end. So if you're trying to do, say, binary classification where you only want 2 elements, this might just represent one particular number, which is a probability, and you can assess it against a threshold. Convolutional neural nets are useful because in the process of applying this kind of very long and complicated data transformation to your original 2-dimensional array, initially they do it by keeping some information about the 2-dimensionalness of this. And there's a convolutional step to this where they take an array which is also 2-dimensional, and they do a weighted sum to apply these data transformations to it. And on the basis of these filters that get applied to your original image, or they get successively applied to it, it can draw out different patterns and different features within your image, depending on the particular, how this array is kind of configured in this numerical space. You could identify things about the edges, sharpen up the image, kind of blur it with a different kind of numerical distribution for the noise. So this will come back up when I talk about the particular examples. It's useful to kind of think of this first in a simpler context. One is, say you just have a representation of a number as an image. And so if you're the post office and you're trying to identify this, whether this handwritten digit is one of the numbers from 0 to 9, you take your two-dimensional array, which represents the image, you apply this set of many data transformations to it, but all with the goal of transforming this two-dimensional array into a one-dimensional array, which has 10 elements, and whichever one has the maximum, you pick that as your class. Now, ideally, hopefully it lands on the 4, because this is a 4. But along the way of applying this, you can see different aspects of this particular image emerging. One, say, is the corners. This might be a continuous set of lines. Here you have lines of a particular orientation. These are more general, then you start getting to coarser and coarser levels of resolution, all the way until you get to your one-dimensional array. This is useful, say, if you're trying to identify patterns within a piece of art. You might try and apply a convolutional neural net and then look at various intermediate states where you can try and see what is it that the convolutional neural net is identifying as important features to draw out of your original image on the way of trying to do some kind of classification on it. To take that like an example of a cat, you might draw out some level of features which are of importance in one layer, and as you keep on getting to higher and higher in an abstract sense representations of a cat, you might combine some of these so that they look like eyes or ears or a nose, and then eventually you're able to get the very high level representation that this is kind of the concept cat. So going back to our applications, this is very useful in object recognition, object detection. This, say, would be a piece of art where you can focus in on particular aspects of a piece of art, and you might try and draw out all of the mouths across a whole set of different pieces of art. And you might try and cluster them together to see if particular artists represent mouths in similar ways. This would be somewhat of a manual process, or you could feed it into a neural net and let a computer do this, and then afterward come in and see if there's any meaning that you can attribute to the particular features that it's identified. This will also come in when I talk about the archaeological artifacts. With the archaeological artifact I'm going to talk about, there's what they're trying to do is identify patterns that exist on sherds of pottery. And with these sherds, the sherds retain imprints of a paddle that was used when the piece of pottery was being constructed. But I'll talk more about it when I get to it. The idea is here you have some kind of pattern that exists on your artifact, and you can apply, say, machine learning algorithms to this to try and first identify what the particular pattern is on this image of the sherd, and then you can try and identify for any particular pattern of lines that you've identified, does it correspond to designs that you've already identified, and if so, which ones? And you could also try and, for those which don't correspond to a particular design that you've already identified, you could take the ones that don't get identified with the design, and then you have your entire set of kind of unidentifiable patterns and see if any of them kind of clustered together and look like they're related, to see if it might indicate a completely new design that hasn't been found yet. So object recognition is, of course, a fascinating topic. Here, this is a neural net applied to just trying to detect people or objects within an image. A very snazzy application of this is trying to come up with self-driving cars. So with self-driving cars, they have to be able to interpret the environment that they're navigating through. They could take images with a certain periodicity as they're navigating through this environment, and they could identify, say, people, vehicles, traffic lights. Of course, you want to be sure that you identify the traffic lights so you know when to stop. You want to be able to very accurately identify people, so you don't run over them. And you have to do this in a real-time sort of environment. So it has to be fast, has to be accurate. Object recognition has some very interesting applications to trying to accommodate differently abled people. So say that you have this large data set of hands doing sign language. You could do object recognition on this so that you could now try and pass these into your image classification algorithm and identify one particular hand orientation or kind of sign for a given letter. And if you're able to do this quickly and accurately, now you can watch a video of somebody doing sign language and transcribe it for somebody who needs transcription of this sign language. Also, if you're for those people who might be blind, say, there are a lot of images in the internet which aren't captioned, which don't have any kind of data associated with them. So if you could take your automated object recognition and go through all of these images which don't have metadata associated with them, you could go through and identify that there's a person here, a man in a certain colored shirt, and there's also a guitar in this image. And you could use then language processing along with it to automate the process of trying to write a caption for an image. Here at UCLA, we're kind of getting more onto the language side now. So here at UCLA with Roy Chowdhury's group and some people I believe in public health, they did research looking at blogs that mothers were a part of and looking at their discussions related to exemptions from vaccinations. So they applied machine learning algorithms to this, natural language processing to it. And they aggregated, different discussions on the basis of the language that was used when mothers were communicating with each other. And they used this to identify a variety of different relationships. You could also identify relationships between different types of people, like parents, children, schools, and government, with other types of objects like vaccines, as well as with other institutions, say like religious institutions. So there might be particular vocabulary that people tended to use when they were between any two nodes on this. There might be particular vocabulary that was used across the set of blogs, and they looked at how information, was contained in this data set. So that's the extent of the examples I want to give. I don't want to go too deep down into that well, because there are a lot of different examples which might be interesting for us to talk about. I think that there are a couple reasons, perhaps many reasons, but a couple that I'll focus on now, which highlight why machine learning is interesting and useful, say, to a particular field of academic research. One is it allows you to identify patterns or to model patterns in a particular data set without having you to manually write a lot of rules to explain this. You might not even know beforehand what the rules are. Maybe there's no good solution to this yet. Maybe, when you're trying to do something like this, conceptually, how is it that you would manually write down a set of rules which would take an image and be able to abstract the particular objects in it? That would be a very difficult thing to write a set of rules for, or even to conceptualize what a good solution to it is. But having an abstract way with a machine learning algorithm like a convolutional neural net will allow you to tackle these complex problems. It can also allow you to deal with fluctuating environments. So if you have the case like spam classification, when spam is being classified, you might be able to do a very good job of sending it into your spam folder. But now the people who are designing spam might figure out how to get around if you're doing this from a rule set, say they might figure out how to get around the rules that you've written so that spam can actually get sent to your inbox. And so there's this continuous interplay between writing the good spam classifier and having people design spam to get around the classifier. And the model that you design has to be continuously updated. So if you're just writing a lot of rules for this, you don't want to keep on writing rules to just deal with these edge cases or the new developments from the people who are writing spam. You want to design your kind of your algorithm or your approach to this one time, and then be able to run it multiple times if you need to. And you can run it on data as it's coming in afresh into your environment, and have the model be updated without you explicitly having to say, here are the particular things that I want to change about it. Machine learning is also very useful for getting insights from a large amount of data. So if you have, if you're trying to read novels for your dissertation, you can read so many novels. It depends on how fast you can read them. But in all likelihood, you can't read 100,000 novels for your dissertation and expect that to be a reasonable thing to do. It's not that close reading isn't going to be useful, and you'll probably get, just as many insights from a very close reading of the novels you're looking at as you would. Well, there's a question about how much useful information you'll get from machine learning. But machine learning will allow you to approach large amounts of data and get ideas about the patterns that are contained in that large amount of data, and it might point you in a very useful direction, which you wouldn't be able to get at just trying to read all 100,000 novels by yourself isn't conceivable. So if you're dealing with large amounts of data, machine learning might be a very good way to try and approach it in order to guide your focus into particular parts of your data set where it might be useful to do a closer examination. Yeah, so I'm going to switch now to a couple examples specifically related to humanities, and look at how machine learning and also how high performance computing can support and enhance humanistic endeavors. Machine learning, I've already described. This helps you to uncover patterns and trends. For example, in analyzing text, identifying and classifying objects and images, there are a number of other things. The high performance computing comes into this because it will facilitate processing vast amounts of data, as well as provide the computing necessary to train the models. So if your machine learning models are very big, it might not be reasonable to train your model in a reasonable amount of time just on, say, your own laptop or on your own desktop machine. It can really help if you're dealing with a lot of data, or if you want to learn a machine learning model which is very large in size or which has a lot of parameters. It can be useful to do the computing on something which has more computational power than just a single computer. But I'll talk now about these three particular examples. One is art attribution, by which I mean taking a piece of art and trying to figure out who the painter was that painted that particular piece of art. I'll talk about distance, listening to Danish radio, and design patterns in these pottery artifacts. So the first one I'll talk about is art attribution. So I don't have the authors on here immediately. This was Alison Langmead and Nygren. These are both researchers at Pittsburgh. Rodriguez and Craig Kerm from the UCSD Supercomputing Center, if I remember correctly. And they were looking at taking pieces of art and looking at this question of trying to attribute a particular artist as the creator of the piece of art. So they looked at Giovanni Morelli, who had, in some sense, a very algorithmic approach to this, although it's not like he was writing code. But he had this idea where his hypothesis was that painters really reveal their identity in the particular piece that they create, where they kind of don't focus a lot of their painting activity. For example, in the fingernails, the hands or the ears or the toes, in these particular places, the painter might not pay as much focus to painting something like the hand as they do to the overall composition, or paying attention to other particular details, which are more the focus of the particular piece of art that they're creating. So he had an approach where he would take these particular items within a piece of art and use it to extract a set of features. And then he would take that set of features and how they were composed in a particular piece of art to compare it across a variety of samples from different artists. And he would say, who draws a hand like this, say, and he would use that identification to do the art attribution. So there's a question, if you're trying to use a machine learning to do this, to try and do clustering or to try and extract features that the machine learning model does to attribute artists, does it use the same set of features as Morelli might have identified? Or does it identify some other features, to doing its art attribution? Does it do it in a similar way that art historians might do it? The answer to that will be no. Or, something different. This is another image, representing different years. And on the basis of these different years, which Morelli had identified, you could identify them with particular artists. So if you feed in a piece of art to your machine learning algorithm and it tries to identify particular features, if you take those features and then you take a particular piece of art and you feed that particular piece of art through your machine learning model and see, is it actually identifying an ear? And is an ear a useful way to discriminate between different pieces of art or to identify an art with an artist? So these researchers did this in two different ways. They took a data set which had approximately 1,866 digitized images. These were high resolution images, and it was a large enough data set. So it was outside the computational capability of just a single machine. So this then led them to do their computing on a high performance computing center, in this case with Exceed. They did it at UCSD. And they also followed through with this process along with help from technologists from Exceed, who helped with the machine learning for this particular project. In the first phase, they used a computer vision technique called the histogram of oriented gradients. We won't get into this, but here, this is taking a particular painting, decomposing it into, say, an individual element like a mouth. And then you could use this particular technique to identify kind of where there's a difference between a dark place and a light place. This was a useful technique to try first because, so it conceptually mapped well to Morelli's method. So Morelli had this method where he would take, some of these elements which he had determined to be good differentiators between different artists, and he would decompose the images on the basis of how those were drawn. So in a sense, his algorithmic approach to trying to do art attribution was similar to this process of trying to extract kind of these regions going from a dark to a light, trying to see how this particular element was composed within the painting. The second phase was to try and apply a machine learning model. So they used convolutional neural nets. This is a representation, another way of abstractly representing that convolutional neural net, where here you're taking the image, you're applying it through a set of data transformations, all the way to try and get it to the end where you identify it with, say, a particular artist or some other kind of class here at the end. The convolutional neural net used a pre-trained VGG19 base. And what that means is that there are convolutional bases to convolutional neural nets, which have already been pre-trained on very large data sets. This one, if I remember correctly, they trained it on the ImageNet data set, which is a very classic data set to try and assess image classification algorithms. This particular convolutional base was already pre-trained on a completely different set of images, but on a very large set of images. And then the usefulness in that is that you can take that, and it has its own set of weights associated with it. But since it's already done object recognition, object classification, generally speaking, if you have another image that you're feeding into it and you want to do object recognition within a new image, it'll do a pretty good job on it. It's already been trained on a lot of images. So they use this pre-trained base, and they also did hierarchical clustering, and they looked at different parts within this convolutional neural net, and they looked at the kind of the pools of the convolutional layers and the pooling layers to try and see, given these two images, say, these two paintings, the convolutional neural net at one particular point was using this as a useful way to differentiate between these two images. And you can see here it's trying to differentiate them on the basis of whether one of them, looks like it has a body, or it looks like it has a body, or looks like it doesn't really have a body that's distinguishable from the background. So they went through and they looked at the different features, and looking at the different features means looking at the different ways that the filters showed up in this convolutional neural net. Ultimately, with both methods, they found that the computer could, reproduce analogous dimensionally reduced representations of the paintings. On the other hand, what the machine learning model produced, what the histogram method produced, were fundamentally different from those of Morelli. So it actually led them to a deeper understanding of Morelli's process, because they had to think clearly about how Morelli was, reducing the representations of a piece of art. And he reduced them in such a way, that matched more cleanly with his subsequent process of trying to look at the context, kind of the historical context of a piece of art and the particular style of the particular artist. He would reproduce it in a way that would cater better to those other parts of his process of doing art attribution. And that was different from the machine learning algorithm, which was only looking at the particular images that were given to it. It didn't have any information about the historical context, information about a wider range of artists or anything like that. This process of computational analysis also led them to discover new questions that they thought art historians might want to address relevant to art attribution. In particular, if you're looking at a digital representation of a painting, what particular meaning do you have to attribute to how a stroke is represented in pixels in the image? That would be an example of one of the questions that they realized might be important to address in this particular, for this particular problem. So I have a couple of my own personal observations from this. One is, it was very key to have experts from different domains. In a problem which is complex like this, you definitely have to have domain experts who are involved in art attribution and art history, who understand at a deeper level how this particular process is carried out, and how attribution is evaluated by other art historians, to set it in the proper context. The high performance computing and the machine learning experts were definitely useful too, because for one, they facilitated the computational needs. They also knew, how to take a pre-trained convolutional base in order to get a very highly effective machine learning model. And they knew the process of trying to extract features from this convolutional neural net. This combination of high performance computing and machine learning, it was a very useful tool to carry out this research, but I think it was also very useful as, in a sense, another collaborator. It served to stimulate new questions for these particular researchers, and it served to crystallize their thinking about what Morelli was doing in the first place. All right, so now I'm going to turn to a second example. The second example, I've called it distance listening to Danish radio. These particular researchers were thinking about how radio has evolved in the context of or in competition with streaming services, that have become prevalent now. Things like Spotify or iTunes have changed how we listen to music, how we might listen to talk radio. What's our motivation for listening to radio versus a streaming service? So their focus was how has a distribution of music and talk on the Danish Broadcasting Corporation's radio channel P3 developed over this very large time span. So this is 30 years. They did some what I call close listening and some distant listening. The close listening would be having them as a person actually listen to it. Taking 5 or 7 particular case studies, say, but only a sample of the entire 30-year data set. The distance learning would be to listen to all 65,000 hours of music, which was on this particular station over 30 years. That's not really conceivable for a person to do. So you do this computationally. You have some automated way of trying to process the image and process the audio signal. In this case, it's audio rather than an image. Of course, if you're going to try and automate this, you have to be specific about kind of quantifying the question that it is that you're asking of the data. Their question was, has there been a shift in emphasis from music to spoken words? They were wondering, whether they could identify a transition when there was a rise of streaming services, or if there were different transitions from music to speech at different points throughout this 30-year history. The distance here in distant listening is because it's done by computational models, simply because the data is too big. The fact that the data is big also leads us into, doing this with high performance computing resources. They also use convolutional neural nets. So they took their representation of sound, kind of an audio signal over 30 years, and they decompose it into different segments, and they represent the sound as a spectrogram in order to do a classification problem. This is binary classification. It's speech versus music. So they have a spectrogram here, which is showing, different frequencies in the audio signal as a function of time. In that sense, you're turning the audio signal into something that's like an image. And now that you have an image, just like with a painting, you can feed this through a convolutional neural net. Now here their focus wasn't on identifying particular features within this. In a sense, it was identifying particular features, but the ultimate goal was simply to do the binary classification at the end, speech versus text. And to do this, they drew on other work that had been done specifically in how to design a particular neural net like this. So once they had this, they were able to look at the audio signals over this 30-year time span and how they were distributed into music versus speech. And then they could look at the change in this, whether they were getting closer, whether they were getting farther apart, whether they evolved in the same direction or in opposite directions, and try and infer possible mechanisms for change. Some of the dates they identified with institutional and media political changes. Sometimes there were changes in musical hosts on the particular radio station that they were looking at. I forget when Spotify and iTunes grew, but there's also the competition with the growth of streaming services. In addition to finding answers to the questions that they, initially set out to look at, they also realized that they could confirm one of the other authors. One of these authors had a previous theory about the radiotization of music, which is that given how music and speech are scheduled on a particular radio station, it makes more sense to fit in a piece of music that's kind of on the order of 3 minutes into a radio station's schedule. In some sense, that informs the creative people who are creating the music. If they actually want their music to get broadcast on the radio, it'll be more ideal if their music actually fits in that 3-minute time range. So there's this musicians create a process which is in some sense constrained or at least informed by the dictates of the demands of the radio station in terms of scheduling. So their computation with this machine learning led them to question the data source too. Actually, they looked here in 2005, and they realized that there was kind of they weren't able to explain this change in behavior purely on things that were happening societally or within the business space. But then they realized that their data source itself had changed. The actual format of how data was stored in the archive changed in this particular year, which changed the representation of data within the archive that they were looking at. And that kind of had an influence here on how their how the algorithm was identifying what was inside of the data. It kind of filtered in indirectly from how the formatting of the data changed. Just like with the art attribution, this computational analysis also led them to ask new questions. They realized, since they now actually had a 30-year span of data to look at, they realized the close listening that they did, this 5 to 10 particular samples of radio time that they listened to closely, did not include any span here from 2016 to 2019, where they also realized that there was an uptick here in the speech. So this led them to investigate a particular time within the particular data set that they hoped to investigate, that they realized they had missed this with a smaller close listening. Now they went in and they reinterrogated this with a more close listening. And they realized that they could identify this. In this particular case, it was because there was a rise in streaming services of trying to draw in people who had certain personalities, that has a certain level of fame within society. All right, so now I'll shift now to case number 3, my final example. And this is looking at archaeological artifact. And for this, I'm going to look at a project called Snow Vision. This is out of the University of South Carolina. So this was that problem that I was talking about, where you're trying to look at design patterns and archaeological artifacts. In the southeastern United States, with the indigenous people creating pottery, they used these paddles, which had a particular design pattern on them, and that pattern got imprinted onto pottery that they were creating. Unfortunately, there's a lot of cultural and historical significance to the paddles, but they haven't survived as an archaeological artifact. They aren't found, but what is found are these sherds of the pottery that existed. So what archaeologists are doing to try and reconstruct these paddles is they look at these sherds of pottery that exist, and they try and reconstruct the design patterns kind of by fitting together pieces of a puzzle in a sense of these, these patterns. There might be a fair amount of data. And of course, there's no reason to expect that any given pair of these is going to fit together or even be related to the same paddle. It can be a very laborious and tedious process to try and do this reconstruction. So the computation comes into this as a way to try and ease the process that the archaeologists are trying to do. There are 2 aspects to this. One is to ease the process that they can use to do the kind of the reconstruction back of the paddle design. So given any group of sherds that you have, you can try and extract the patterns. You have to extract the pattern in the first place, and then try and match it either with known designs, or if you can't match it with known designs, try and cluster them together to try and indicate whether there's a completely new design here. Another aspect of this was setting up computational infrastructure where archaeologists could access a front end through a website, a front end service, and then also access a storage service on the back end, which would store both data and metadata about these sherds and about the paddle designs. kind of serve as a backend for all these services that they were designing. So that was kind of a novel aspect of this too, just designing this gateway infrastructure. They use a very large number of machine learning models too, some of which were these convolutional neural nets, again, because these are images here that you have to do, you have to be able to recognize, say, these particular pattern lines within shirts. You then have to be able to try and match them up against design patterns that might already exist. Or if they can't be matched up, you can also use machine learning to try and do clustering. So you have some data set of these patterns which haven't been matched with a given design, and you try and figure out whether some of them look like they match together, whether they look like they form a kind of common cluster. They tested a lot of models and they found some good options that gave accurate results, but it's definitely not at the level of full automation. This still requires, archaeologists to come in, and even after all the machine learning process that's going on, the archaeologists have to come into this and kind of do some final steps themselves. So in this case, the machine learning is rather serving like a useful assistant. There's, there are a lot of patterns here. There are a lot of combinations to try and sort through. So the machine learning is doing a very good job of reducing some of that laborious process that they would otherwise have to go through. Even something like the clustering. If the clustering can simply point them in the right direction to identify a particular pattern, that can be a very useful thing for the archaeologists. There are definitely complex challenges that still remain. Sometimes the lines don't overlap. It can be noisy data. You're trying to reconstruct these patterns from photographs you're taking of actual artifacts. So there are challenges here which challenge both the archaeologists, but also that challenge people approaching this from a computational and machine learning standpoint. So there's an interplay here where the technical developments are driven by the archaeology, and the archaeology drives vice versa. Right. So those are my three examples. I don't want to go too much over time, so I'll kind of breeze through this. I assume if you're coming to this talk, you might have some sense of what high-performance computing is. High-performance computing is, in a sense, the aggregation of computational resources in order to enable you to do computing at a much more significant scale than you could just do in a traditional computer. So you get clusters or supercomputers or some kind of distributed computing platform, which is the device now which serves as your kind of big computer on which you do the computing. They can achieve performance that's millions of times faster than you get on your traditional computer. And really this scale has several key advantages. One is you can have access to many more processors, and if you're able to do your computing in parallel, that can really speed up the work. If your computation takes a day to run normally, and even if you feed it onto 24 simultaneous processors, now they could achieve the task in an hour, generally speaking, relative to it taking an entire day to run the task. These are connected with a high-speed network, and a lot of the machine learning libraries too are really built to do efficient parallel computations. So in particular with deep learning and with neural networks, the libraries are really designed to run on GPUs, and it can be very advantageous to do highly parallel computations for these neural nets, which can have lots of weights that you have to learn, and it can be very useful to try and speed up the computation that you do. So they can be advantageous simply in the data processing stage. If you're dealing with very large data sets, or if you're dealing with very complex data sets, which take a lot of time to simply process and massage before you can even do the classification or whatever else it is you need to do in the first place, the HPC can simply be advantageous in terms of trying to manage and massage and pre-process your data. They can also accelerate machine learning training because you can do parallel processing. Data processing in general is faster, has better capabilities for handling large data sets. Now, all of these make high performance computing very advantageous. And hopefully you got a sense of that too when I was describing the particular examples as to why their demands drove them to seek out computing with high performance computing. I think collaborations between high performance computing and machine learning definitely advance research in both fields. So very large machine learning models, to some extent, you can only conceivably train them on large systems, depending on their scope and their size. And also machine learning and deep learning in particular help to drive the development and use of these graphical processing units, the GPUs, or other advanced hardware architectures. There are definitely challenges in trying to combine these three together. One is that it really does take a team. Each one of these comes with its own special skill set, and humanities, has any number of fields, each of which has its own particular domain expertise. So if you want to do research across all three of them, usually it'll take a team of people who are really highly skilled in the particular combination you're looking to achieve. That might not necessarily always be the case, but it will at least be useful to seek out advice, I think, from people in all three. Another challenge is for people who are coming from the high performance computing or the machine learning background, dealing with humanities data can definitely feel less familiar than working with your standard kind of tabular data sets or data sets that are familiar from scientific and engineering data. Those data sets which high performance computing has been catering to for a long time are and more homogeneous, usually numeric. Usually they can easily be generated in large sizes with some kind of automatic or simulation process. The humanities data is much more heterogeneous, fuzzy, can be interpretable, transcribed by researchers. So there's a challenge there in dealing with just dealing with the data itself. And there can be challenges just in communicating between the different people who have different kind of paradigms and concepts about how to speak about some of these common terms in computing or data. And of course, well, I don't really have time, but care must be exercised to mitigate biases. If you're dealing with personal data, you have to worry about security and privacy, document your processes, and et cetera. So I'll kind of, I'll end here with just an advertisement for high performance computing at UCLA. So I work more directly with a high performance computing cluster called Hoffman 2. Has over 20,000 cores, a lot of memory, does have some GPUs. So if any of you who are attending this are very interested in trying to do humanities research on the Hoffman 2 cluster, I definitely invite you to reach out to myself or to Francesca, or to Andy or to Ryan or any of us. There's I'm sure I'll be able to, well, maybe not help you out with your research, but at least help you approach computing on the Hoffman 2 cluster, or hopefully address other questions that you have about doing high performance computing or machine learning on it.